So hi everyone, my name is Sylvester and I'm going to present an overview of the Engineering Center. I'm going to walk you through all of the points presented here. So the visual concept we already have here is from previous presentations. The structure of the Engineering Center is divided in 3 floors and inflatable structure. So let's start. We have internal design here. One of the on this slide here, one of the biggest challenges when it comes to creating settlements on other planets is building a safe space to live. I'll explain later on what safe means. Whether it's on Mars or on the moon, space settlers will have to live, work, and sleep in an environment of extreme temperatures without oxygen, while being bombarded with radiation and micrometeorites. And there are quite a few existing designs of habitats. One I see potential in underground habitats, and the one we see here is proposed by Redworks, adapted from construction principles of ancient cultures, such as pit houses and pueblos, as well as natural constructs, like the shell of the Nautilus. So although it's impossible to gather direct information on the interior of Martian and lunar lava tube candidates, scientists have the possibility to investigate their surface expression through the analysis of collapses and skylight morphometry and their arrangement, and compare those findings with terrestrial analogs. So the structure could be built upwards from the base of its excavation pit with multiple levels organized around the central support shaft. Both Mars and lunar caves, as large as entire towns, could provide shelter for human exploration. So caverns on the moon and Mars can offer enough space, protection against cosmic radiation, stable temperatures for astronaut bases, and researchers compared hundreds of underground formations on Earth, the moon, and Mars, while on our planet, the diameter of lava tunnels, lava tubes, typically ranges from 10 to 30 meters. Some of these fissures could reach more than 800 meters in diameter under the structure of the moon. Pretty much enough space to host a human colony. Lava tubes on Mars and on the moon turned out to be 100 to 1,000 times larger than those on Earth. In addition, why it might be a good idea is that one of the problems we experience on Mars is dust. On this slide here, we see NASA's Curiosity rover that has beamed back pictures of a dust storm that has engulfed much of Mars over the last, over 2 weeks, and prompted NASA's Opportunity rover to suspend science operations. However, the Curiosity rover, which has been studying Martian soil at Gale crater at that time, is and was expected to remain largely unaffected by the dust. Opportunity is powered by sunlight, which is blotted out by dust at its current location or at that time. So Curiosity has a nuclear-powered battery that runs day and night. However, if we decide to settle Mars, there is a chance or option that we'll use different kind of batteries, and dust most likely will affect some of those solutions. Here we can see the Curiosity rover that took selfie in the middle of a dust storm on Mars. So it's pretty bad for the people, but also electronics. So the conclusion here is that for establishing a colony, we need electronic components, robots, and human explorers, and all of those are threatened by solar radiation, interstellar cosmic rays, micrometeorites, which are dropping rapidly, and things like dust and extreme, temperatures in some situation, or temperature fluctuations. And tubes, lava tubes, could provide not only refuge for astronauts, but also protection and safe environments for robots, electronic devices, and things like that. This is, this is presented or proposed by one of the space agencies. It shows the moon, but similar solution might be, utilized or designed on Mars. Moving forward, researchers and designers in previous missions proposed several different internal designs. Inner space design of the infrastructure is very much essential, and it should be 3D printed. Their internal design should have 8 feet in diameter, and it might be, or should be vertical, sitting on the dusty and rocky surface of Mars. Habitats would have 3 floors with spiral staircases inside, sealed hatch for entering and exiting the pod in a spacesuit in the ground floor. Kitchen and plant growing, a plant garden at a higher level, and sleeping quarters would be included as well. Interior design should be airy, light, comfortable for the people. Each floor should have at least 1 window covering the full 360-degree panorama, but should keep the crew from harmful solar and cosmic radiation. Astronauts could use the mobility chassis called Chariot without a pressurized cabin. By riding in rotating turrets, they wear spacesuits while driving this type of vehicles. At least 2 vehicles should be presented for the over extravehicular activities, such as collecting and bringing the ice and minerals. Also, there should be a garage and ground floor and supply mining and water treatment to the crew. The internal design must have 3 circular structures. Division of inner area consists of below parts, which you can also see on those slides here. So the previous slide I presented, that was engineering facility area and specifically ground floor. And as you saw before, we had that that main area. It's a main area of the engineering workshop. Includes the 3D printing area where printing design is integrated. It also has a spacesuit dust removing area where dust is removed mechanically and then magnetically from the spacesuit of astronauts when they come back. And there is an engineering workshop maintenance with having a garage for supplies and collection of minerals and ice and things like that. A washroom is attached to the engineering workshop. There is an upward spiral stair for going to the next floor. Then on also here we see it's a first floor, and pretty much it's data communication and cultivation area. So this floor is actually it includes the kitchen to make and preserve the food. It also has molecular biology and bioinformatics labs to test the food. Cultivation areas have the most food micro production system to preserve the food. Then the other component, which is quite important from my perspective, data and communication center is actually making the connection to the whole station and Earth. It also uses to make the reports and design of the whole project, and upward stair is used to go to the next floor. Then moving forward, so here see what we can see here is actually living area. with some social activities arrangements. It includes the bedrooms and social entertainment area, kitchen, washrooms, and a medical health area. The medical health area has an ICU and isolation room for critical patients. Okay, so moving forward, here, what we have here, Mars missions are a chain of innovation with modern and innovative proven technologies. Scientists and astronomers found new possibilities for great exploration, like the MOXIE instrument located inside the rover's body, and convert the CO2 into oxygen's Martian atmosphere. So in the Ingenuity Mars helicopter is pretty much a small autonomous rotorcraft to test powered flight in the thin Martian atmosphere. One of the great machines and technologies is N3 descent and landing technologies, including the range trigger, giving the parachute precise timing. And the range trigger technology shrinks the rover's landing ellipse and allows it to land closer to the target area with great accuracy. Another technology is terrain relative navigation, which helps to avoid hazardous terrain. Then another one might be the advanced aeroshell sensor package, which helps record what the spacecraft has experienced during its landing and performance. The entering area comprises two main dust removing technologies and remove the dust from astronauts suits when they astronaut suits when they come back. So the first part comprises the brush rollers and that remove the dust mechanically and drop it over the floor. The second part includes the mini platform, which use dust magnetic property to gather it in a bag. Then here also, we can see on this slide here, possible resources to generate in situ or transported from Earth. And it's a complex wide topic, but to give an overview, various possible resources could be found on Mars and transported from Earth if they are not collected directly on Mars. And in situ resource utilization is collecting, processing, and storing and using found or manufactured material. It could be life support, propellants, construction materials, and energy to a space crew, like solar cell production, produced from the lunar soil materials. For example, the materials used to produce solar cells are silicon, aluminum, and glass, and these are present in high concentrations in lunar soil and would be used to produce solar cells. And also construction materials will be required for the colonization of Mars, like local buildings, materials such as regolith. So Mars soil is highly mixed with epoxy resin and tetrodoxylislame, which produces high flexibility parameters and high resistance and strength. So in situ resource utilization uses the Sabatier reaction to produce methane, which is used as a propellant. And oxygen is produced from water by electrolysis, and hydrogen is recycled back to the reaction. And food preserving items and machines are transported from Earth, but most of the food is produced on Mars in the food microproduction floor. Moving forward, here we see management slide. So regarding the organizational structure, the way I structure that is we have engineering center, then chief engineer, researchers, technicians, and assistants, including visitants. So to give some overview, the chief, the engineering center chief, is responsible for studying how the in situ practices are going on. Will monitor each and every section of engineering center, like data center, workshop, rover maintenance, and things like that. Also, he's the person to be contacted directly from the Earth, as well as other facilities in case of any engineering requirement. Then researchers, those people are responsible for carrying out the data research and viable communication using data relay systems. Also will be responsible for doing research on Martian surface by taking use of rover. Then we have technicians in the middle. They will be responsible for spacesuits related activities. As I said before, also will take care of 3D printing processes and maintenance of rover, as well as communication systems like antennas. And we have assistants. Those people will work under chief and are responsible for stack management. Also can be contacted in any case, in case of a tool or equipment is required. Later on, after the base grows, we might need a more complex structure, and our organizational structure might include the overall designing committee and their team members, which carry out projects and respective responsibilities. The main facility chief or committee head might have 3 different managers, including the engagement manager, director, consultants, scientific consultants. Then, the project director might have its project manager and deputy project manager, but again, that's later on. So scientific consultants will be connected to all the project managers. Moreover, the engagement manager will be connected to and collaborate with a deputy project manager to have some development discussions regarding projects and scientific activities. So here on this slide here, positions, astronauts profile and duties. Like I said on this slide here, there are various positions, not only the astronauts according to the engineering facilities required on Mars, scientists, CS engineers, technicians, microbiologists, and other people, will work together to break the barriers, achieve the impossible, as I said on the slide. So profile of engineering center chief must have multidisciplinary, with excellent management and industrial experience. That person should have high leadership capacity with great personal resilience. Its duties should be inspection and control of daily ongoing activities, and the engineering center chief should be responsible for proposing routines and operational protocols with reports daily submission to the main station. Also, that person should design the SOP for the smooth functioning of the station while coordinating with other facilities. And to recap, researchers might have engineering and science background with excellent research and development experience. Those people should be problem solvers. Their duties include the development of new technologies and upgradation and improvement of existing technologies. Maybe one more thing about technicians before we move to the astronaut training program. Also, the technicians must be from an engineering and technology background, maintenance activities experience, also providing the service and managing all the site installation tasks, repair and maintenance, things like that. There is one more important thing. They also repair and charge the electric vehicle so that extravehicular activity can be performed. So they are responsible for diagnosing the errors and technical problems during the flight, and providing its proper solutions. Potentially some IT engineers. Also, those people have duties to make the design, installation, and maintenance of things like computer systems, robot systems, and they will troubleshoot, test, and configure the hardware, software, and other networking systems to meet the expectations and needs. And maybe there's one more thing, microbiologists, those people, we need those people as well, and they must conduct complex research projects and improve sterilization procedures. Also, they develop new drugs to combat fatal infectious diseases. They also perform the duties of lab experiments to diagnose the illness and its better treatment. So moving, focusing on this slide here, astronaut training program. The astronaut training program is obviously well designed and to develop the essential knowledge and skills required for formal mission training upon selection for a flight. They undergo complete 2 years of training and evaluation period. They undergo different physical and emotional tests. They learn many things other than science, just like medical training in case of emergencies. They are trained to be able to cope with the challenging living environment on Mars. They also train to study Mars geology and exobiology. And the astronauts training program is it's a pretty unique training program of working in microgravity, which presents its challenges. Training programs familiarize the astronauts with each complex and highly specialized flight vehicle, equipment, different type of robots, and suit to simulate a microgravity working environment with its own challenges. And so it's just like an educational training program where different learning stages have been developed to train the astronauts for extravehicular activities. Moving forward, here is a slide with a few YouTube videos. Astronauts are usually trained through the design training program. During their training, they also get familiar with the working environment of Mars through different type of videos and workshops. They show them the real working environment of Mars. They got to know the space aircraft's actual internal working operating system, and train different teamwork projects and various extravehicular activities. So here are 3 videos you might watch after this presentation. Moving forward, resources needed for 1 week. Obviously, astronauts use water, oxygen, food to survive on Mars. And moreover, it's not possible to send all of those from Earth. And here's the point: therefore they must produce all those or most of those on Mars. Water is extracted from the soil. The landing of the rover is selected, and also base is selected on the water availability in the soil. The life support units perform water extraction. Soil is deposited into a water extractor, which hits the soil, and water is evaporated. So this evaporated water is condensed and then stored. At least 50 liters of water per astronaut is required for 1 week. Oxygen can be produced by splitting the water into its constituent parts. Therefore, oxygen can be used to provide in the living units. A portion of oxygen can be stored in reserve to be used when less power is available. Then nitrogen can also be extracted directly from the Martian atmosphere by the life support unit. Food required for the astronauts can be transported and stored in a life support unit. However, the stored food from Earth can only be used as an emergency ration. So astronauts prefer to eat as much food as they produce on Mars, but most likely no more than roughly 2 kilograms per day. Food can be produced indoors under artificial lighting, as there is available soil for plant growth in the original habitat. A thick layer is of Martian soil will protect the plant from radiation. Carbon dioxide is available from Mars atmosphere, and water is available through recycling of the water extraction process. A required volume of the soil is investigated and suggested in the simulation outpost to produce food. And this aims to reduce the food that is transported from from Earth. Moving forward, here we have guidelines to be provided to other facilities, entire station. I listed just a few, three. There should be some basic guidelines provided to every crew member and should be followed strictly. There should be regular research and development activities in terms of required facilities, so that the project's completion should be successful. The chief of facilities staff, will have daily routine meetings that discuss ongoing activities and project to run smoothly without any problems. And first of the 3 points, emergency guidelines. So entire crew groups have been should be trained well to deal with emergencies. Every astronaut is informed about the project's integrated process and has been assigned with the respected tasks. The second one, health risks guidelines. In this case, they are guided with various health risks and guided to survive in outer vacuum space travel. They are also well trained and well guided in the International Space Station and Martian bases and things like that. So they know what they will do when they get to Mars, and they know how to react and behave. The last point here, equipment and process risk guidelines. They are guided on using the data reports and 3D printer for the smooth running of projects. Optimum work distribution per floor is well informed and guided on to the entire station, so that an uncertainty on any floor can be well known on an immediate basis. Moving forward, we have protocol section. So regarding protocols, specific routines and protocols of the facility are required and are most important during the operation, as I said on the slide. But there must be maintained regular contact with the Earth via DRS, which is data relay satellite, so that the whole structure of the center should be monitored, pretty much daily. The spacesuits which astronauts use must be dried of dust whenever they go out, and rover should be checked every time before use. Everything that is of daily use should be placed back in its position every time after they use it. So data reports should be maintained and back up regularly. The machines like rovers, electric vehicles, and 3D printers should not be overloaded during their use. The facility must ensure all specific routine protocols. And also, if we use lava tubes, we might have a protocol describing or stating that after each usage, after each use of a robot or rover, we put that rover in a lava tube in some type of safe place to protect that from potential risk, like the dust and things like that. Moving forward, protocols of safety. So obviously there should be some safety protocols, when you work on Mars, but there should always have a daily routine environmental disinfection check and balance. Always go through the air chambers for cleaning purposes when astronauts come back from an external mission, or interact at other centers if we have those. They must have a fire detection system and also a specific control system for it. The crew always has a backup power system in case power goes down. And all the space crew members should have frequent hand disinfection, and they should have an automated system for the environmental and components disinfection. Moreover, have frequent simulations of emergencies. And safety for extravehicular activities is also, necessary to avoid any uncertainty, or critical to ensure a safe landing, human and rover locomotion. There should be a 3-dimensional terrain morphology map, of landing and operation zones. At the landing site, the Martian regoliths, specific range of mechanical properties should be characterized effectively. And then different properties like regolith strength, stability, sinkage properties like, bearing strength, yield strength, or bulk modulus, and the internal friction angle should be determined when with in situ experiments. Moving forward, here we have entertainment type of slide. But to be more serious, it's a protocol for occupancy and entertainment. So those kind of protocols for entertaining astronauts and their occupancy should decrease the stress to have a cool and comfortable atmosphere. Social gatherings with potentially smooth music inside the space habitat every regular day would be a significant step towards decreasing the chances of depression while working in isolation. So a small movie room, having rest facilities with a complete music scene, would be just great. Also, the cultivation activities and social areas can be organized, like you see on some of those pictures here on this slide. An exercising activity would be great to keep them mentally and physically fit. Let's move forward. Food production, protocols for food microproduction. So this is something very, very interesting. Protocols for food microproduction are, like I said here on the slide, extremely important. To have a specific check and balance over food availability for the crew members. But to say a few more words, there is a microproduction floor where food is preserved. Therefore, food logistics must be regularly checked and calculated. And every crew member uses the available food according to need, and there should be a management system to recycle it. Every week, the risk management system should look at the available food, and necessary precautions should be maintained to avoid the extra losses of food items. What you can see here on the slide on the right side, it's some NASA's scientists' work in the crop food production research area of the space station processing facility at the NASA's Kennedy Space Center in Florida, as far as I remember. So the first growth test of crops in the advanced plant habitat aboard the International Space Station yielded great results, which was fantastic to hear. And what you see on the left side top, those are some type of small flowering plants related to cabbage and mustard, and it grew for about 6 weeks, and dwarf wheat for like 5 weeks or something like that. Moving forward, protocols for 3D printing. That's something very, very interesting. All Astronaut should have check and balance over the printing waiting line, as I said on the slide here, but they should organize and decide a specific printing time, and they should test the material and pay attention while making a progress report that shows all the amount of material used while working on a particular project and the amount of material left behind or available in the spacecraft or base. So 3D printers should be maintained and should have routine checkups as per requirements. Spin-offs. So let's talk about technologies and outputs that could be applied to Earth. Different useful technologies can be applied to Earth, and as I say, their outputs would be significant in terms of quality Mars missions. But to say a few more words, like the supercritical Brayton cycle technology in coal-fired power generation, the Earth is one of the greatest of the great technologies. Also, the waste material refilled 3D printer is the technology of pretty much industry 4.0 on Earth. Then we have the dust removal systems, can be very effective and productive technologies that can be used in car washing activities, the place where people are mining. These technologies and their output can be pretty much beneficial while being applied to Earth. Some guidelines to be applied to daily life on Earth. So there are many general and some specific guidelines that should be provided to daily life on Earth. As I said on the slide here, these guidelines can be beneficial for the better assessment of the projects on Mars, but there should be much investment in the new projects as the investment in research today will give a lot more comfort and betterment of the projects and research in the near future. So this is a great way to sustain life, as the technologies and development in the industrial field are much more required. Also, waste management activities must be practiced regularly. Moving forward, SDG, which are sustainable development goals. Improvements in the infrastructure of the operating and developing new technologies will substantially impact sustainable development growth. But what does that mean? These results will have a more significant effect on economic growth, and it will help out to reduce the waste, reuse it and recycle it. So therefore, the waste material recovery facility will be improved. Also, there will be no more energy consumption systems, as new technologies and development systems will be introduced to use less energy and be more efficient and environmentally friendly. And here are some references and my contact. And thank you very much.